A groundbreaking discovery in Japan has turned the world of solar energy upside down. Researchers have achieved something that sounds like it defies the very laws of physics. In a study published in the Journal of the American Chemical Society, they measured a result that challenges the long-established rules governing solar cells. This compound, when applied as a thin layer on existing silicon solar cells, enhances efficiency without requiring any redesign of the panel. The silicon underneath continues to function at near baseline efficiency, even if the new material degrades. This could revolutionize the way solar energy is harvested. What makes this discovery even more astonishing is that it's not just one team making these claims. Independent research groups in Japan, Australia, and the United States are all converging on this same concept, each approaching it from different angles. The world's top solar panel manufacturers are backing this research with funding. Yet, despite all this promise, no commercial product exists yet. The lead researcher himself has warned that, despite the breakthrough, it may take years before we see anything practical from this technology. The research team's work has been described as a challenge by the lead researcher, who made it clear that, although the science behind the discovery is real, turning it into a commercially viable product will take time. The most optimistic timeline currently put forward by any scientist is 5 years for a small-scale laboratory proof of concept. But what exactly is this quantum phenomenon, and why does it take so long to develop? Let's break it down. The core concept here is a process known as 130% quantum yield. At first glance, this sounds impossible. It refers to a material that produces more than one usable electron for every photon of light it absorbs. This is not some simulated result from a lab experiment. It has been measured and confirmed in real-world conditions. And importantly, it doesn't rely on drastic changes to the existing silicon solar cells. All it requires is the application of a thin layer of this new material, which could work with current manufacturing processes. But despite the breakthrough, there's a catch. It's not ready for immediate deployment. The key to understanding this discovery lies in the Shockley-Keyser limit, a theoretical limit that has governed solar energy efficiency for over 6 decades. In 1961, William Shockley and Hans Joachim Quaeser calculated a theoretical ceiling for the efficiency of silicon solar cells. Under perfect conditions, that ceiling is around 33, 7% efficiency. But when you factor in the inevitable losses in the system, the practical limit drops to about 29, 4% efficiency. Every silicon solar panel ever made has been bound by this limit, but the Shockley-Quaeser model makes one critical assumption, that each absorbed photon generates at most 1 electron. This assumption was challenged back in 1965, when scientists discovered something remarkable about organic crystals like anthracene. They found that some materials could produce 2 excited electronic states from a single absorbed photon. This phenomenon was called singlet fission. However, it wasn't until 2006 that researchers like Hanna and Nosik published calculations showing that if you could harness singlet fission in tandem with silicon, the Shockley-Quaeser limit could be surpassed. Essentially, it would allow 1 photon to generate 2 electrons, which could dramatically increase efficiency. The race was on. However, the problem wasn't creating the additional excited states. It was capturing them. A process known as first-order resonance energy transfer, FRET, kept stealing these excited states before they could be used. For over 20 years, every attempt to harness this extra energy failed because most of the excitants were lost in the process. That is, until a team from Kyushu University in Japan and Johannes Gutenberg University in Germany made a breakthrough in March 2026. In their collaboration, an exchange student named Adrian Sauer introduced a molybdenum compound from the MINT lab to the Kyushu team. This turned out to be the key. The team found that they needed an energy acceptor that could selectively capture the triplet excitons produced by singlet fission without being disrupted by the parasitic FRET process. The molybdenum compound's lowest energy state, a spin-flipped Di6 state, could only be reached by the triplet pathway, not by FRET. This allowed the energy to be captured efficiently and transferred to the silicon. To fully understand why this matters, we need to take a closer look at the inherent losses in a traditional silicon solar panel. Despite being an engineering marvel, silicon solar cells are far from perfect. In fact, they leave a substantial amount of the sun's energy untapped. These losses occur in specific areas. Thermalization. Loss. When a high-energy photon strikes the silicon, it carries more energy than the silicon can use. The excess energy is turned into heat, which wastes roughly 30% of the energy that could have been converted into electricity. Subband gap transmission. Photons, carrying less than 1. 12 electron volts pass right through the silicon without being absorbed. This is the infrared portion of the light spectrum, which accounts for another 20% of energy that silicon cannot utilize. Carrier recombination. Silicon also suffers from unavoidable recombination of charge carriers, which further diminishes efficiency. As a result, most silicon panels today achieve only 22 to 25% efficiency. In fact, the world record for a single-junction silicon cell certified in early 2025 sits at 81%. This shows that the ceiling for efficiency is fast approaching, and improvements within the current framework are minimal. Heat-driven degradation. Solar panels operate much hotter than the standard testing temperature of 25 degrees Celsius. At typical operating temperatures of 42 degrees Celsius, silicon loses about 6 to 8% of its efficiency due to heat. Over time, this thermal stress can result in measurable degradation of the panels, reducing their output. The capture problem. Even when singlet fission successfully splits a photon into two excitons, the competing process of fret typically pulls those excitons away before they can be used to generate electricity. This has been the major bottleneck for 2 decades. The breakthrough with the molybdenum-based energy acceptor directly tackles this capture problem. And by solving it, the researchers also addressed the other efficiency losses. The most important of these is thermalization, where the excess energy from high-energy blue photons is no longer wasted as heat, but is instead used to generate additional excitons. These triplet excitons can be efficiently transferred to the silicon, where they generate electron hole pairs, converting what would have been wasted energy into usable electrical current. Moreover, singlet fission also helps surpass the Shockley-Keyser limit. It allows for the high-energy portion of the solar spectrum to generate 2 electrons from 1 photon, increasing the theoretical efficiency ceiling. The work published by Diber and colleagues in 2021 suggests that the theoretical efficiency could rise to somewhere between 32, 9%, and 34, 6%. Some speculative calculations even suggest that with fully optimized band gap matching, the limit could reach as high as 45%. In short, this new approach could completely change the landscape of solar energy, taking us from where we are now, stuck in the low 20s, to much higher efficiencies. The traditional silicon solar cell has reached its limit, and this new technology offers a path beyond those constraints. In terms of thermal efficiency, reducing heat inside the solar cell is crucial. A team at the University of New South Wales in 2021 modeled a tetraene on silicon module that ran 4 degrees Celsius cooler than the standard silicon module under the same conditions. This modest temperature reduction translated into an increase in the projected field lifetime by 7 years, representing an improvement of 9%. The UNSW team, working with a more stable material for fission, DPND, has estimated that this lifetime extension could go up to 4.5 years. The fourth key contribution from the March 2026 study directly addresses the long-standing capture issue. The Kyushu University and Mines University teams paired singlet fission tetracene DRS with a molybdenum complex, which has a spin-flipped D6 state. Here's why this is important. The energy gap between the spin-allowed channels and the spin-flip state is such that the parasitic pathway becomes energetically uphill and inefficient. But the energy transfer from the triplet excitons generated by fission to the D6 state is exothermic, meaning it flows downhill. This means the parasitic energy transfer is blocked, and the productive transfer to the silicon is favored. For photons absorbed between 112 and 132 eV, D6 excitons are captured successfully. However, there's still one limitation that hasn't been addressed: the subband gap transparency. Singlet fission works with high-energy photons, specifically in the blue and green portions of the spectrum, but it does not affect infrared photons below the silicon band gap. These infrared photons still pass through the material unused. Additionally, the recombination of carriers at the silicon contacts remains unaffected. A fair evaluation of this technology must acknowledge that it improves silicon's ability to harvest blue light, but does not enable it to capture light that it couldn't absorb before. Now, what do the actual experimental results say? The Kyushu University Mines University paper reports data from 3 configurations of tetracene DRS paired with the molybdenum spin-flip emitter. The phenylene link dimer achieved a quantum yield of 112%, with a margin of plus or minus 6%. Meanwhile, the p-terphenylene linker reached a yield of 128%, with a margin of plus or minus 4%. These results were obtained using steady-state and time-resolved fluorescence spectroscopy, with near-infrared emission serving as the readout signal. However, it is important to stress that no solar cells were built in this experiment, and no electrical current was generated. This was purely a chemistry demonstration in a laboratory flask, not a functioning solar device on a rooftop. To put this in context, other groups have come closer to integrating singlet fission with silicon. In 2019, a team led by Marcus Eininger and Mark Baldo at MIT applied tetracene directly onto a silicon wafer with a very thin 8 angstrom layer of hafnium oxenate to passivate the interface. They reported a combined fission efficiency, factoring in triplet to silicon energy transfer, of 133%. However, despite this, the cell's overall power conversion efficiency remained below that of a commercial silicon panel because tetrazine only absorbs a small part of the spectrum and degrades when exposed to air. In 2025, researchers at UNSW published the first demonstration of triplet exciton transfer from a stable singlet fission material, DPND, into crystalline silicon. While this solved the degradation issue, it still didn't result in a device that outperforms a standard commercial cell. No singlet fission-based solar cell efficiency has yet appeared on any official record or chart. The 132% quantum yield observed in the March 2026 study comes from a single paper, a single consortium, and a specific solvent system. It has yet to be independently replicated, and as Dr. Jin Zhang pointed out to New Atlas, quantum yield can exceed 100% under certain definitions. However, this does not equate to an energy efficiency greater than 100%. This distinction is crucial. The technology is still in its early stages, but it does offer structural advantages over competing technologies like perovskite silicon tandems. One of the main advantages is drop-in compatibility. Perovskite silicon tandems require a tunnel junction and precise current matching between the two subcells, which adds complexity. The singlet fission layer, on the other hand, simply adds photocurrent in parallel with the existing silicon cell. According to Ben Carworthen at UNSW, in theory, you would only need to apply an extra layer on top of the existing silicon architecture. No fundamental redesign is necessary. The second advantage is graceful degradation. If the organic singlet fission layer deteriorates over time due to sun exposure, it becomes optically transparent. The underlying silicon continues to generate power at its original baseline efficiency. In contrast, degradation in a perovskite tandem cell can reduce the output of the entire system. With a singlet fission-enhanced panel even after aging, the silicon portion remains effective. Another notable benefit is the abundance of materials. The core components, carbon, hydrogen, nitrogen, oxygen, tin, are all common and widely available. The hafnium used in the MIT interface layer was only needed in a tiny 8 angstrom thickness. Molybdenum, a key material in this technology, is cheaper and more plentiful than traditional materials like ruthenium or iridium used in photosensitizer chemistry. Additionally, the flexibility to substitute metals like chromium or vanadium broadens the material options even further. DPND can also be deposited at low temperatures, making it compatible with roll-to-roll manufacturing, a process that could lower production costs. Despite these promising developments, the cost of this technology is still uncertain. Currently, there is no commercial product available based on singlet fission. No price has been set because the technology is still in development. Any claims about a $50 heat glass or 130% efficiency panel available for purchase are misleading. These are not real products and have no basis in any peer-reviewed studies or credible announcements from researchers in the field. As of now, the technology that is commercially available is conventional silicon-based solar panels. In the United States, residential solar installations typically cost between $2.50 and $3.50 per watt before any incentives. The modules themselves cost roughly 30 to 50 cents per watt, a significant drop from $5.92 per watt just 4 years ago. The federal residential solar tax credit, which provides 30% off the cost of a solar installation, will be available through 2032 under the Inflation Reduction Act. However, it will end for residential installations after September 30th, 2025. For commercial or utility-scale developers, the investment tax credit is still available if construction begins by July 2026. Now, what would the impact of singlet fission technology be on the cost and efficiency of solar panels? Hypothetically, if a fission coating added just 5 percentage points to the efficiency of a module without adding any extra manufacturing costs, the absolute best-case scenario would be that a system's payback period could be reduced by that same proportion. For instance, a system that would typically pay for itself in 8 to 12 years might instead pay for itself in 7 to 10 years. While this would be a meaningful reduction, it's not transformative for individual homeowners. The cost target that the ARENA ultra-low-cost solar program, which funds the UNSW effort, has set provides a clearer picture of where this technology is headed. The goal is for modules to reach greater than 30% efficiency and cost less than 30 cents per watt by 2030. While this is an ambitious target, it hasn't been achieved yet. So, what does this mean for you? If you're considering installing solar, sticking with conventional silicon technology remains the best option for now. The current state of solar technology is mature, with costs reaching historic lows. However, singlet fission, despite its potential, is still several years away from transitioning from laboratory experiments to proof-of-concept models on silicon wafers. In fact, it's likely over a decade before any practical product will be available for residential installation. Waiting for singlet fission to be commercialized is not a viable strategy for those seeking solar solutions today. It could delay an investment that is already financially feasible in the present. So, what is standing in the way between the lab results in Kyushu and a finished solar panel on your roof? The first major hurdle is the technology readiness level. The spin-flip emitter system is currently at TRL 3EE, which means it has been demonstrated as a proof of concept in a controlled laboratory setting, but it has yet to be tested in real-world conditions. Meanwhile, the DP&D on silicon system is between TRL 3 and 4, still far from being ready for commercial application. In comparison, perovskite silicon tandems, the main competing technology, are already in the TRL 6 to 7 range. Oxford PV plans to ship residential solar modules with a certified efficiency of 5% by late 2024. The gap between TRL 3 and TRL 9, which represents a fully certified, mass-producible, and commercially viable product, is measured in decades rather than years. It's a long road ahead before singlet fission can achieve that level of maturity. Another significant challenge is material stability. While tetrazine, the classic molecule for singlet fission, degrades in air through a process known as endoperoxide formation, DP&D from UNSW has solved this specific issue. However, the molybdenum spin-flip emitter brings new concerns. The stability of these metal organic complexes in thin film form, especially in the presence of air and moisture, has yet to be fully studied and published. The next hurdle is the solid-state gap. As Nuro Kimuka, senior author of the study, bluntly stated to PV Magazine in April 2026, achieving robust performance in solid-state solar cells remains a major challenge. All of the measurements in the Kyushu study were conducted in a solution phase, but moving from a dissolved molecule to a solid-state film on a silicon wafer presents a completely different set of engineering challenges with no clear timeline for resolution. The fourth obstacle is interface engineering. MIT's research demonstrated that the passivation layer between the organic material and silicon must be incredibly thin, around 8 angstroms, which is approximately 4 atoms in thickness. This thin layer plays a crucial role in the overall performance of the system, but controlling such a thin film at a manufacturing scale remains a precision challenge that is yet to be solved beyond the lab. Next comes the issue of certification. Currently, no certification path has been established for singlet fission-enhanced modules under the IEC 612, F15, or 617 standards. These standards require extensive accelerated lifetime testing to predict the 25-year outdoor durability of solar panels. No research group has yet conducted these tests for singlet fission technology. Another major barrier is manufacturing scale. UNSW is working with industrial pigment manufacturers to scale up the synthesis of DP&D. But scaling the molybdenum NHC emitter to gigawatt-scale production volumes remains untested. According to the most optimistic timelines from researchers in the field, we could see a small-scale lab proof of concept for silicon modules by around 2030, with mass production potentially beginning by the mid-2030s, contingent on solid-state yields being consistent. So, what does this mean if you're considering a solar investment in 2026? The safest choice remains conventional monocrystalline silicon, particularly from Tier 1 manufacturers like LONGi, Jinko Solar, JA Solar, Trina Solar, and Canadian Solar. These companies offer 400-watt class panels with 22 to 25% efficiency, and they are the most reliable option available for residential energy investments today. This is not some consolation prize. It's a proven, bankable technology at prices lower than ever before in history. What should you be cautious about? Avoid anything marketed as a singlet fission solar panel, 130% efficiency modules, spin-flip solar boosters, or quantum yield energy glass. No such product currently exists, and if you encounter these terms on a mass-market online retailer, it's either a misrepresentation or a flat-out scam. A key red flag is when marketing materials conflate the terms quantum yield and energy efficiency. If a seller uses these terms interchangeably, it's a clear sign that they don't fully understand the physics behind what they're claiming to sell. In that case, your best course of action is to walk away. Some credible research teams to watch include Omega Silicon, a UNSW spinoff that has secured a $4.8 million grant from ARENA and has partnered with Jinko, JA Solar, LONGi, Canadian Solar, and 4 other manufacturers. Another notable group is MIT's Baldo Lab, which continues to develop Exanon silicon devices, as well as the Kyushu Mines collaboration, which is behind the spin-flip emitter paper. These are all legitimate academic and institutional programs producing peer-reviewed science. They are not, however, selling products. Here's a specific threshold to keep in mind. Once any research group publishes a certified solar cell with a power conversion efficiency, not just quantum yield, for a singlet fission-sensitized silicon device that exceeds the current single-junction silicon efficiency record, or if any group publishes a 1, 0.0-hour outdoor reliability test for a singlet fission silicon module. That will mark a significant step forward. Until one of those two milestones occurs, the best approach is to watch with genuine interest, but continue investing in conventional silicon today. When singlet fission technology reaches production, and it very likely will, based on the underlying physics, you'll be able to evaluate its viability. The areas where singlet fission will matter most are in hot, high-radiance climates. Think places like Arizona, the Arabian Peninsula, India, and Australia, where the cooler running advantage provided by reduced thermalization can combine with intense baseline sunlight. In such regions, every degree of reduced cell temperature leads to measurable power gains over the span of 25 years. Singlet fission will also make a difference in space-constrained applications, on rooftops with limited space, building integrated photovoltaics, and electric vehicles, where watts per kilogram and watts per square meter matter more than cost per watt. A 5% efficiency boost can significantly alter the economics. However, in cold, overcast climates with ample roof space, the impact will be less noticeable. Conventional silicon already operates near its temperature optimum in those conditions, and adding another panel is likely a more straightforward solution. It's also important to note that the architecture of singlet fission isn't a tandem system like perovskite silicon tandems. There's no second junction, no need for current matching, and no tunnel recombination layer. The design consists of a thin organic film applied during cell fabrication with a passivation interlayer beneath it. Retrofitting this technology onto panels already sealed under glass isn't practical. It would need to be incorporated during the manufacturing process. Maintenance would be the same as standard silicon cells, and the only question remaining is the organic layer's lifespan. In unencapsulated lab tests, current organic materials for singlet fission last only a few years. For commercial deployment, these materials will need robust encapsulation to extend their lifespan. Alternatively, it might be accepted that the singlet fission layer gradually becomes transparent over time, causing the panel to revert to baseline silicon performance. However, warranty structures for this dual aging process have not been designed yet. At its core, this is a converging story. 3 different research groups are solving 3 different pieces of a 60-year-old puzzle: selectivity in Japan, stability in Australia, and interface engineering in the United States. The underlying physics is sound, but the timeline is long. As someone evaluating energy technology, it's crucial to understand the difference between a chemistry breakthrough and an actual product launch. Now, you do. If you value honest technology evaluations, subscribing and sharing will help make sure this content continues to reach those who need it. Meanwhile, another team has already succeeded in pushing a commercial solar cell past 34% efficiency using a completely different approach. Perovskite silicon tandems are already being shipped, and they are reshaping the economics of every rooftop that receives direct sunlight.